All right, I think this is my cue. Hello, everyone. Thanks for joining me in this session. Wow, so many people. Nice, especially considering they have cookies in one of the other rooms. Only HTTP cookies, but still. Welcome to Flight of the Flux. This session about how Project Reactor works, a deeper look at reactive programming through the lens of Project Reactor. Since there are so many people here today, I'm curious, how many of you know about reactive programming, Project Reactor in general? Like have some exposure. All right. How many of you do use that on a day-to-day basis or in production? Or okay. So initially, this talk was more tailored for the later. It's kind of suppose that you have a bit of exposure to the concepts of Reactor in general. I'm not going to do an overview of the API and all that. Let me introduce myself first. I'm Simon. I work for Pivotal on Project Reactor. These days I mainly work on the core. We have a few other projects around Project Reactor core, like Reactor Native for the networking aspect. But I mainly work on core. And today I'd like to teach you a bit about, of course, Project Reactor there, but more precisely about a few concepts, like the fact that nothing happens until you subscribe, what we call assembly time versus execution time. The difference between a hot publisher and a cold publisher. We'll see how Reactor is concurrent agnostic. We'll see how it offers tooling to hops from one thread to another with stuff like publish on, subscribe on, and the concept of schedulers. We'll look at something called work stealing, so we'll go deeper into the bowels of the library and look at how it implements patterns like work stealing. What does that even mean? And also, we'll look at operator fusion, another interesting optimization. So, first, let's go back a bit to the basics, since not everybody is using that stuff on like every day. Project Reactor is built around the reactive stream specification, and it's a library that allows you to compose asynchronous processing pipelines in a declarative way, and then you subscribe to these pipelines and you let your data flow through these pipelines and transform and split and merge back, all sorts of operations, all in an asynchronous, non-blocking way. The gist of the reactive stream specification is that you have something called a publisher and something called a subscriber. So the publisher emits data. As it becomes available, it pushes data to the subscriber. So the publisher is like a loudspeaker, and the subscriber listens to what the publisher sends. Another key concept is the specification defines a number of signals and how the publisher and the subscriber interact. So what you can get is what we call the on-next signal. An element becomes available, it gets pushed to the subscriber. Maybe a few seconds later, another element becomes available, a new element becomes available, it gets immediately pushed to the subscriber. And then at some point, this sequence of events, it completes. So a reactive stream, it's 0 to n on next signals or events pushed to the subscriber, followed by, at most, one complete. Or could also be an error. So the error signal is something that is terminal. It's the end of that particular sequence, right? But it's a first-class citizen, so it's not throwing something into thin air. An exception won't disappear. It's part of the specification. So you ultimately get all the data before the error happens, and then you get the error. So you know that something wrong happened. Yeah, same stuff. You can push elements and then get an error, of course. So there's publisher, subscriber, and actually there's something in the middle, which is called the subscription. So the publisher gives that subscription, to the subscriber, and the subscriber can use that to fine-tune the volume, if you will. So the subscription allows you to express a demand for data. You say, okay, I'm only ready to consume, say, 10 elements. I know I have the processing capability to process 10 elements. Push them to me as they become available, but don't push more than that, because otherwise I would get overrun. So fast publisher, slow subscriber, it can adapt through the subscription, the request. And also that subscription object that you get, it can be used to cancel the whole pipeline from end to end. So yeah, that's basically reactive streams. And Project Reactor is a direct implementation of that. So the types, the reactive types that we offer, Flux and Mono, are publishers. But of course, the reactive stream specification is kind of an interoperability specification. So it doesn't define a whole API. So if you were to use that directly, it would be really hard, because you would have to factor in a lot of moving parts, and a lot of the value of the specification is in the actual specification, not the interfaces, but the set of rules that you have to follow to interoperate with any implementer. But Project Reactor offers a very rich API on top of that. So the idea is that we provide a lot of operators that can be composed, like functions. And by composing these, you declare what you want to do in your pipeline, every step of your asynchronous processing. And then you start pumping data through that, and it will transform in a non-blocking manner. All right, so far so good? Good. So, the first item I wanted to present was the concept of assembly time, and the concept that nothing happens until you subscribe. That's kind of one of the first mantras that you should learn about Reactor and kind of reactive programming in general. So nothing happens until you subscribe. What does that mean? So we generally say that you have two kind of steps in the life cycle of a publisher, of Flux or a Mono. And the first one is assembly time. It's basically instantiation of a Flux object. So here, let's say you have a test suite, and you have an initialization block. So before each test, you want to initialize a Flux. So you will say, okay, I have a variable, my Flux. I'll assign to that flux.just of foo. So it's basically, it captures the string foo, and whenever you are interested, it will emit foo to you. And then the next step is it will emit foo actually to map, and it will transform that into the length of that particular string. But if you do that, actually, nothing happens. Why? Because you haven't subscribed. So there's this basically a Flux or a Mono. It's lazy. So when you talk about execution time, you talk about subscription time, if you will. Much later on, you could have passed this Flux instance around your application and maybe enriched it with other operators, or I don't know, like conditionally building the pipeline. But it never emitted foo in the first place, and you've passed it around, and it ends up in one of your tests in this case. And in your actual tests, that's where you call .subscribe on this myFlux variable. That's where it triggers the whole pipeline, basically. So, of course, this is a very, very simplistic example. But if your original Flux, the source Flux, was something like an HTTP client that performs an HTTP request, a GET, in the init method, it wouldn't perform any network call. It would only start performing the HTTP GET at this point where you call subscribed. And then it would push the result asynchronously to the next step in the pipeline, which would transform it, extract it, and you would end up with a transformed value that is derived from this HTTP call. So that's interesting, because since all of this is happening in an asynchronous way, what would you see in a stack trace if there was an error? Would you see where would you see a trace of that init block where the Flux was instantiated, or would you see something else? Actually, you would see something like that. Okay, well, it's a big stack trace. Let's try to get the interesting parts. Oh no. So you see, you have a division by 0, but where does that come from? You see that an onNext happened, so maybe it happened in there, but where does the 0 come from? So if you go deeper in the stack trace, you start seeing stuff like request, subscribe, flux.subscribe, and you end up here. You end up at the point where you are subscribing in the test, but you don't see any trace of this init method that I was showing earlier. So it stops at the point where you subscribed, and you get less information out of the stack trace due to the asynchronous nature of all that stuff. It's a bit like, I don't know, you prepare a runnable somewhere in a field, and then you schedule it, you submit it to an executor, and if something happens, then maybe you don't know where the runnable came from in the first place. A good tip is use checkpoint. We try to improve on that aspect, and with a few operators and a few hooks, you can actually attach more information about the assembly time to your Flux. And by doing that, once you get an exception, it will reattach that information, like it's an additional stack trace that shows you exactly where the data, the value came from, and not only where it blew your code. So yeah, by doing that, you attach more information, but it has a cost, because that's basically an additional, we have to instantiate stack trace on the operator, on the checkpoint operator, or even on every operator in your sequence. So there's a bit of a challenge here, but that's something to keep in mind still. All right. The second aspect I wanted to talk about was this concept that there are hot publishers and cold publishers. So hot versus cold. What is so far we talked about cold publishers actually. What is a cold publisher? It's a publisher that when someone starts listening, generates the data and emits the data when it's available can take a few seconds, but it's triggered by someone, a new listener, a new subscriber. And if a new second subscriber comes in, it will generate a new set of data and send it to that subscriber. And if a third subscriber comes in, it would generate a new set of data and send it to the subscriber. The analogy with the HTTP request example, it would perform 3 gets, basically. So 3 times the network call. So that's why we say nothing happens until you're subscribed. And it's always true until it's false. Enter the hot publisher. So the hot publisher, on the other end, it doesn't really care that there are 1 subscriber or 3 subscribers on 1,000 subscribers. It can be triggered by the first subscribers, but once it starts generating data, it sends the same data to everyone. So you can kind of share data. So if you don't want to make a 3 HTTP call or 1,000 HTTP call each time a new subscriber subscribes to your web client, for instance, you could turn that into a hot publisher, and it would send the same data once, perform the network call only once. So that's the main difference. And it applies mainly to the sources, like the publisher, and not intermediate operation in a sequence. But there are operators that will turn a hot publisher into a cold publisher, and vice versa. For instance, you can do caching, you can do sharing of a sequence, and that sort of stuff. So, yeah, these are key concepts when you start your reactive journey. Often, at this point, you start wondering, in terms of threads, how does that stuff work? And the answer generally is that, well, Reactor is concurrent agnostic. So, do you have to accept a particular execution model? The answer is no. We provide tools to fine-tune on which thread you want to execute, but generally it doesn't force you adopting anything. But frameworks, of course, and libraries built on top of Reactor, of the core Reactor library, they might be more opinionated, of course. There's one exception. You might notice that there are a lot of time-related operators as well. So generating a time interval, a delay, kind of the reactive equivalent to a thread.sleep. And these need to change threads because otherwise they would be blocking the main thread. So everything is non-blocking when you do flux.mono.delay and say, okay, I'll send a signal in 10 seconds. It doesn't block the thread for 10 seconds. It schedules a task on a particular thread, the parallel thread pool. But it's just scheduling that task. It's not actually blocking the thread or the CPU. It's just enqueuing that task. And the other important aspect is it needs to do that because it doesn't really know if you are on the main thread or if you are already on a separate thread. So if they need to change threads, how do they do this? What's the abstraction? So we introduce the schedulers abstraction. And a scheduler is an interface that is part, kind of representing a thread pool or an execution model, and also represents the clock. And that's quite important because it allows us to do interesting things like in testing, we have a virtual time scheduler, and that clock aspect, it's actually in your hands with this particular scheduler. So if you are doing a test of a sequence, a pipeline, a processing pipeline that transforms the data but also introduce some delays, like it runs on a source that emits one element every day and then stops after 10 days, but you're only interested in testing the transformation that it will apply to these elements, then you can use the virtual clock of the virtual time scheduler and do that sort of test of the complete sequence transformation in a few hundred milliseconds instead of waiting for days, which I don't recommend in a unit test. So that's the main abstraction. It abstracts the clock and it abstracts the scheduling of tasks. And the main operators that use that concept are publish on and subscribe on. So let's start with publish on. When I say Reactor doesn't impose any execution model on you, but instead offers tools, that's what I'm talking about. In your sequence, very, very easily, you can say, okay, I will receive something, I will perform a first transformation, and then I will go to, let's say, the the swing thread to show an alert, because everything UI has to happen in a dedicated thread. And then I will shift back to a thread pool and do more computing, etc., etc. So in the middle of your chain of transformation steps, you can very easily switch a subset of that pipeline to a particular thread. And that's done by chaining in a publish on. So it would look like that. You have a Flux source, and you apply first operator, OP1, OP2. You chain in publish on in the middle, and OP3, OP4, and then you subscribe. So what happens in terms of threads for each of these operations, each of these steps, 1, 2, 3, 4? The thread in which you call subscribe is where your data starts flowing. When you subscribe, there is a signal that traverses the whole chain up to the source and tells the source, okay, I'm interested now, start emitting data. And by default, naturally, the data will be generated and emitted in the same thread, so the blue thread. So OP1 doesn't do anything with threading, it's just let's say, a transformation. It runs on the blue thread. OP2 runs on the blue thread as well. And then enters publish on. And when publish on receives something, it will switch to its scheduler provided thread and emit that same data on that new thread. So we switch, at this point we switch on the orange thread. And then OP1 will run on the same orange thread and OP4 on the same orange thread. So yeah, the thread calling subscribe is where data flows initially. After calling publish on, so only on the right hand part, that data flows in the second thread. Compare that to the second interesting operator, subscribe on. So if you do exactly the same processing pipeline, except you switch publish on for subscribe on, what happens? Well, this happens. Subscribe on, it changes the thread where the subscription is performed. And that subscription signal, it flows upwards to the source and say, okay, I'm ready, I'm listening, please start emitting data. But by that point, it's already on the orange thread. So OP1, OP2, but also OP3 and OP4, they are executed. These steps are executed on the orange thread. And this is because, as its name suggests, it subscribe on changes where the subscription happens. And as we saw previously, that's also where data starts flowing. What about the two together? Want to try a guess? So, if we have subscribe on in the chain, followed by publish on, and we subscribe to that. And by the way, when you subscribe, you can also pass in a lambda to say, okay, the final form of my data, that's what I want to, that's how I want to consume it. So, if it was byte arrays in the Flux, the first in the source, but OP1 and OP2 and OP3 and OP4, they finally transform that, refine that, apply Jackson, for instance, deserialize, and you get a user object. Then this lambda in the subscribe, it gets, that's what it gets, a user object, the final form of your data. So, care to guess what happens in terms of threads? What we get is something like this. So we execute the subscribe in the main thread, the blue thread, but then it starts sending this I'm interested signal upward of the chain of operators. But then when it traverses the subscribe button, that changes the thread to the orange one. So that goes back to the Flux, the source, runs on the orange thread. OP1 runs also on the orange thread, OP2 as well. And then we hit, on the way back, we hit publish on. And there we switch to a third thread, the green one. OP4 does its transformation on that third thread. And then you get the final form of your data. And it's passed to the lambda. So the lambda actually executes in the green thread, even though the subscribe was executed in the blue one. Yeah, that's what we get. So you see here something interesting. Subscribe on, it influences operators on its left, but also on its right, but also on its left. So if you have only a subscribe on in your chain, it influences the whole pipeline. Publish on the other end, it influences execution, like the runtime, on its right. So subscribe on both sides until it reaches a publish on at some point, and then it switches. A question that I often get is, and how can I go back to the main thread? Once you've switched. Unfortunately, you cannot, the main thread, the one named main in Java, you cannot associate that to a scheduler. You cannot capture that. You cannot submit tasks to the main thread. So once you've run off the main thread with a publish on, then you cannot go back to it. But you could go back to a dedicated single-threaded scheduler if you wanted, or the swing thread, or anything that is that accepts submission of tasks. Yeah. Speaking of submission of tasks, what if I told you that also these schedulers, they can steal from each other? Not like that, of course, but yeah, I wanted to talk about work stealing. Where do most operators run again? They run on the thread, like the thread from, by default, the thread from which they received their data. So when an operator receives an on-next signal, it processes that same signal on the same thread, unless it's a special one like publish on. So what's work stealing? in some cases in Reactor, we have operators that combine data, that can combine data from several flux or monos, several sources. And these sequences, they could also be executed in separate threads. So let's say we are joining two streams, and one is executing transformations on thread 1, the blue one. The other is performing other transformations on the orange one. In that sort of cases, we have generally a pattern called a drain loop. And we have a shared queue in the middle that is used very, very briefly, and it's a bounded queue, so it doesn't grow indefinitely. But it allows to do what we call work stealing, and it goes like this. The first, like the orange thread, receives a new element. What it will do, it will push that element to the queue, which is thread safe data structure in this particular instance, of course. So it will offer that element to the queue, and then it will perform a comparent set atomic operation, and to check that nobody is already working on that queue. And if it detects that nobody is working, that it will start performing the work on that element, or rather, it will poll the queue and start working on the element it gets from the queue. So here it would be the same one. But what if, while it's still performing its work, the blue sequence also received an element? Then it will also offer that element to the queue, but it will immediately exit. It will detect that the orange sequence is already performing work by checking that guard, doing that comparent set operation, and it will just it will do much less. It will just offer the element to the queue and say, okay, somebody is already working. I have nothing else to do. Meanwhile, the orange sequence is still working. It finishes working. It sees that it still have it's still one. It's the one that did the work. So it will inspect the queue and pull from it and say, okay, in the meantime I've received one new element. So it will cycle back and perform the work on that second element as well. So basically the heavy lifting is done by the orange thread, which is busy looping. Well, it's not busy looping, it's actually doing some work until the queue is exhausted, and by that point it will release it will flip back the atomic guard and say, okay, I'm done. First one that receives a new element, maybe in 1 second or sooner, will win again and perform the bulk of the work. So yeah, at that point it exits. So the idea here is avoid any problems with concurrency and all that, and also being more efficient, because that orange thread is hot. It's already performing some work. It's already taking benefit from the CPU architecture and all that. So it will do its work on a loop, and there will be less thread switches that way. There is still a bit of it, but it's much less. So that's work stealing, and that's basically, you don't see it, but it's an optimization in Reactor that is in place to make all that stuff blazing fast. The other optimization that I wanted to talk about is operator fusion. So what do we mean by that? So we have two types of fusion. The first one, the easiest one, is macrofusion. And macrofusion is very simple when you think about it. If you have 3 times the same operator in a row, for some operators, of course, then Reactor, since we have the assembly time versus execution time, Reactor will be able at assembly time to detect that and say, okay, this is basically you want to apply the same operators with 3 different transformations. So you can combine that into a single instance of the operators. So you have less steps in your pipeline. You are still applying all of the work, of course, but you have less operator instances, and that's interesting when you look at the stack trace as well, because it gets less deep. Even though you have a more complex pipeline, it keeps things a bit more manageable. So yeah, quite simple. But the other one, the more interesting one, is Microfusion. And what we call Microfusion is an optimization that works on operators that are not the same. So Microfusion, it needed to be the same operator as a map, for instance, or a filter, or what have you. But Microfusion, it actually works on a sequence like this, where you have a map, a second map, but then you do a completely different operation, a filter. So you transform once, you transform a second time, and then you filter out some data. But also, what is the Microfusion? In a sequence like this, by default, you would have on each operator, you would have a dedicated bounded queue that is there to act as to manage what we call the back pressure. So this volume button that I was talking about, at the start. So we need to instantiate such queues, bounded queues, per operator, or even actually per operator's time subscribers, because each time you subscribe, it basically generates a new chain of subscribers that does the actual work. And with Microfusion, what we try to achieve is avoid that entirely and instantiate a single bounded queue that traverses that subset of your pipeline, so that elements are passed to the different steps more efficiently. So yeah, the idea is, again, it's an optimization. It's only for operators that are compatible between each other, but that's detected automatically, and you don't have to do anything to benefit from it. The other interesting aspect is that it allows to kind of bypass some back and forth with the requests. So it allows us to avoid doing too much ceremony around requests, so how many items you are interested in, especially if one of the operators in the middle changes the shape of that request, like if you have a buffer operator, or if you know that you want only elements in bulk or stuff like that. Yeah. So, single transverse bounded queue. So, yeah, that's the kind of optimizations that Reactor performs under the hood. If you want to have a look at the library, it's all on GitHub. It's all open source, and you'll see pretty interesting patterns. It's kind of hard to digest because that's not something that a lot of Java developers are accustomed to, like working with atomic field updaters or stuff like that, and performing compare and swap operations. But it's really interesting, and that gives the library a very, very good performance. In some instances, thanks to the fusion, when you have only one element in your source, we can kind of, that allows us to detect that and reach almost the same performance as if you had returned the value directly. So it's quite important to have that. Yeah, that's basically all I wanted to present today. So yeah, that's all for me. I think I have 10 minutes left for questions. So if you have any question, feel free to raise your hands. Yep.
Is it possible to achieve multi-threaded operation in a map operator with one subscriber?
Is it possible to parallelize a map processing in a map with one subscriber? Not really, because the reactive streams specification says the on-next element, they must not be concurrent. But you can, you have a parallel operator, so you can divide and conquer, have a divide and conquer approach where it will split the data on 2 or more parallel rails, and each rail will execute on its own thread that you instruct. You instruct it to execute on its own rail, and then you can apply maps in parallel and join back at the end.
So, and how the items in a stream will be spread into this parallel?
It's round robin, yeah. We might add something more configurable, sorry, at a later point, but.
What do we do if we use a flat map, and in a flat map we use a publish on, and in a publish use like scheduler.
What about flat map? And if you inside a flat map you use scheduler, publish on. Flat map will allow you also to. It has a parameter for parallelism, so it will which allows it to subscribe to up to n inner Flux or Mono inner publishers. And if each of these publishers runs on a separate thread, it's perfectly fine. It will, but it will result in these elements being emitted on their respective threads, basically.
Each of the
yeah.
Of the flux will be in each particular thread.
Yeah.
In a publisher.
Yeah.
Thread that I published. Yeah.
Yes. I think there was a question. Yeah.
I have exceptions at runtime because I was doing things to cold or hot streams that weren't possible. Is there a good reason why you can't see from the type if it's hot or cold?
So the question was, I got exceptions at runtime because I was doing mixing hot and cold and that sort of kind of sources. And can we do something to detect if it's hot or cold in the first place? Yeah, it's true. Technically, maybe we could. Like, it's technically feasible, but it all depends on the architecture and the way this is all implemented. Makes it quite difficult to have that sort of information encoded in the types. And the types is all what you get. The difficulty is past. You can look at your parent operator basically, but you cannot really look at past that. So if your hot source is 2 operators away from you, then tough luck. You cannot detect that. There is a set of operators that deal with, so that causes problems with back pressure basically. I guess what you had, the type of error that you had was on back pressure exception. There are a set of operators that are made to deal with that. If you know that you might have a very chatty source that kind of ignores the requests, like you cannot tell it to slow down because it's too hot to handle. you can chain in some operators that will say, okay, if it emits too much, maybe I want to buffer a bit, or maybe I want to drop the extra elements. If it's data from a sensor, for instance, and you are only sampling, you can perfectly drop the extra data that way. But you could also buffer up to a certain amount, then drop or something like that. So it's on back pressure, something. All that set of operators are there for that. Another question? Yeah.
I missed the first part of your presentation, so perhaps you already explained it, but I was wondering what was the main reason for the creation of Project Reactor while we already have something like RxJava?
Okay. So the question is, why Reactor when we already have RxJava?
They're quite similar, right?
Yeah. So RxJava and Reactor are indeed quite similar. If you talk about RxJava 2.
Yeah.
And actually, so the timeline for reactive programming on the JVM was this. Originally, all that stuff comes from the .NET world with reactive extensions. And then someone at Netflix figured out, hey, that's a pretty cool way to keep the expressiveness and conciseness while doing asynchronous code easily. So Ben Christensen imported that from the .NET world to the Java world with RxJava. And the reactive stream specification that I was talking about at the start of the talk, it came up only later on. And it came up from an effort of RxJava was involved, but also vendors like Pivotal, Aka, Leiden with Aka, I mean, I forget. Well, anyway, it was a joint effort to produce this reactive stream specification, and the main idea of the specification is that there will be several vendors, and we want to be able to interoperate between these libraries. So around that time, there was a very strong coordinated effort with the guys in the RxJava team, and the Reactor team and the RxJava team work closely together on this implementation. So this is very, very, very similar. The thing is, RxJava, they made some decision that went in another direction, and also they have all this legacy of RxJava 1 with a certain numbers of operators that they had to have as well. Whereas Reactor was more of a greenfield in that aspect. So yeah, that's one of the reasons. But it's very, very similar indeed. Nowadays, it's getting less and less similar because the concepts and the architecture are similar. But in RxJava 2, you get only one publisher. It's Flowable. And on top of that, they had single completable. Like nowadays, it's like 5 total reactive types, 4 of which are not back pressure enabled. Whereas in Reactor, we decided from the get-go, there's always back pressure, and we have 2 types only: Flux, 0 and elements, or Mono, 0 or 1, which encodes a bit of semantics in your types. So yeah. Unfortunately, we don't have much time left. Thanks for listening. Thanks for joining me. I hope you learned something. Thank you.